So far in this chapter, we have reviewed the Lewis model of bonding and VSEPR theory. Both of these models are pretty useful. The Lewis model tells us about how many bonds an atom can make when it combines to form a molecule. Similarly, VSEPR theory tells us about the bond angle. Whenever an atom combines to make a molecule, what will be the bond angle or what will be the shape of the molecule. However, none of these two theories really explain why atoms have to combine to make molecules. Why do they even make covalent bonds? And they don't really tell why energy is released when atoms combine to form molecules. To answer these fundamental questions, an entirely new approach or entirely new model was proposed, and the name of this model was quantum mechanical model or wave mechanical model. The beginning of a quantum mechanical model was provided by Albert Einstein. Einstein postulated that light consists of photons of electromagnetic radiation. The energy E of a photon is proportional to its frequency, and energy of photon can be expressed by this equation, E equals h nu, where h is Planck's constant. This theory was, or this postulate from Einstein was revolutionary because until that time, the light was considered to be a wave. However, according to this Einstein's equation, light is behaving as a particle. In 1920s, a French physicist named Louis de Broglie followed Einstein's lead and advanced the revolutionary idea that if light exhibits properties of particles in motion, then it is possible that a particle in motion should exhibit properties of a wave. He proposed that a particle of mass m and the speed v has an associated wavelength lambda, and this is the equation he proposed. It's extremely revolutionary because now Louis de Broglie is saying that particles can also behave like a wave, just like a wave can behave like a particle. Later, Erwin Schrödinger built on the idea of de Broglie and proposed an equation that could be used to describe the wave properties associated with an electron in an atom or a molecule. So this equation is known as Schrödinger's wave equation. Schrödinger's wave equation led to a new branch in physics known as quantum mechanics or wave mechanics. Quantum mechanics is the branch of science that studies particles and their associated waves. Solving the Schrödinger equation gives a set of solution called wave function, and wave functions are denoted by a Greek symbol psi. Each wave function is associated with a unique set of quantum numbers, and each wave function occupies three-dimensional space, and it is called an orbital. The square of wave function psi or psi square is the probability of finding an electron at a given point in space. A characteristic example of a wave is shown in this example. This kind of a wave can be obtained from a particle such as plucking a guitar string. The mathematical equation to express this wave is called wave equation. The wavelength of this wave is measured from top of a one peak to the top of adjacent peak, and or it can also be measured from the bottom of a trough to the bottom of next trough. So this will also be same as wavelength. The numerical value of the solution of this wave, which is psi, or the wave function, can be positive or it can be negative. But remember, uh, when we square it, its value will always be positive. It can also be zero, but it can never be negative. And we learned in previous slide that square of psi is the probability of finding the electron in the area around the nucleus. So in other words, the orbital can never be negative. So psi square is orbital. So the value for orbital is always positive, or it could be zero. The value where psi square is zero, that place is called a node. So node is a point in space where the value of solution to wave equation is zero. And the nodal plane is a plane running through the node. Quantum mechanics is quite complex, and it is a quite vast branch of science, and the entire quantum mechanical model cannot be explained or understood at this point. So for most aspect of organic chemistry, it is best to consider the wave-like properties of electron. In this course, we will concentrate on wave functions and shapes associated with S and p orbitals, because they are the orbitals most often involved in covalent bonding in organic compounds. So when we describe interactions between orbitals such as s orbital combining with p orbital, actually we are referring to interaction of waves. Now waves can interact constructively or destructively. If two waves interact constructively, they overlap in such a way that they enhance the effect of each other. For example, if one wave is combining with another wave constructively, so these two are combining, so the resulting wave will be a combined wave with, so this is called constructive interactions of wave. If two waves combine destructively, so for example this wave combining destructively, you will see that they are opposite to each other, and the resulting wave will be much smaller phase. So the positive phases and negative phases will be higher. So these are the positive phase and negative phase, and in destructive interference, the positive and negative phases will be lower or zero depending on the two waves. As I mentioned earlier, that in organic chemistry, we do not generally focus on the solution of an electron wave, or we don't really care about the wave functions. All we focus on is the shape of atomic orbitals, and in those orbitals also mainly will focus on s and p orbitals. So this picture describes the shapes of s orbital. Remember, when we solve an equation, we get wave function psi. Psi itself doesn't have that much meaning, but when we square the psi function, we get probability of finding the electron around the nucleus. Now, what does that mean? It means is that if this is my nucleus, and the psi square will tell me the area in which finding the electron, there is a maximum probability of finding the electron. So for example, for s orbital, that area is somewhere here. Now the dots I'm drawing here are not electrons. The dots are probability that the electron can be here, can be here, or can be here, or can be here, can be here. There's only one electron, but there are 1,000 probabilities that it will be here. For example, if I'm at home at night, the probability of finding me is highest in my home. I could be in my bedroom, I could be in the bathroom, I could be in my living room, but I'll be in my home. So my home is the orbital, kind of, right? Because that's where, if I'm the electron, so that's where the probability of finding is maximum. For example, nowadays, during the COVID lockdown, our homes are our orbitals. Why? Because that's where we can be found. That's where there is a maximum probability that we will be there. So that's the definition of orbital. Now, according to calculations, uh, see, the probability can be, see, electron, there is a very little chance that that electron can be far outside also. For example, there you see those tiny dots, but the maximum probability is somewhere here. So we just cut off the line where the probability is 95% or high. So that part is called orbital. So this is the s orbital shape. The 2s, so around the, so this is 1s. So around the 1s there's a nodal plane. Nodal plane means where the probability is 0. And then encapsulating this one, there's a new probability map which comes up. And this new probability map is, it's again sphere, again new probability. So this new one, this one, that's 2s. So this represents 1s orbital. Around the 1s is 2s. And in between 1s and 2s there's a nodal plane. Nodal plane means the probability of finding electron is 0. So the nodal plane in this case is this side is the nodal plane. This is the shape of p orbital. When quantum mechanic equation is solved, there are three solutions for 2p orbital, and these three solutions are shown here. Although these are the probability maps, but we generally show p orbitals like that. So this section is this one, and this section is this one, and that's the nodal plane. So probability of finding the electron right in the middle is 0. So this is this one, and then this one. So one is px, py, and pz. This is the cartoon representation of p orbital. Remember, we do show p orbitals separately, but in reality they are all together. For example, if let me see, so if this is the nucleus, around the nucleus we have let's say this is the s orbital, right? And then around the s orbital we have, that's one s orbital. So then around the one s orbital, now we have 2s orbital, and then we have px, right? And then we have py, and then we have pz. The point is that all the orbitals are around the same nucleus. So that's how they can overlap with each other also. So nucleus is so in this case nucleus is somewhere here inside, right inside there is a nucleus. So the Schrödinger wave equation, which is the basis of quantum mechanics, it provides ways to determine the shapes of atomic orbitals. Now it also provides another useful information, and that is to quantify the energies of covalent bond formation. Now these energy calculations, or what we call approximations, have taken two forms. One is called molecular orbital theory, the other one is called valence bond theory. Both of these theories calculate the energy uh, released when atomic orbitals combine to form a molecular orbital, or in other words, when atoms combine to form molecules. Both of these approaches will calculate the energy of that system, and we will see in a while that in both approaches, whenever two atoms combine, there is a net release of energy which provides stability to the system. Hence, that is the driving force why which explains why atoms combine to form molecules. So the first approach is molecular orbital theory. So let me clarify one more time. Both of these theories of chemical bonding use the methods of quantum mechanics. But each of these theories makes slightly different assumptions. The valence bond theory provides the more easily visualized description of single bonds, whereas molecular orbital theory is most convenient for describing multiple bonds. In actual practice, the model for bonding that most organic chemists use is a combined theory, which is combined valence bond and molecular bond approach. Let's talk about molecular orbital theory. This theory begins with the hypothesis that electrons in atoms exist in atomic orbitals and assume that electrons in molecules exist in molecular orbitals. Just like we used the Schrodinger wave equation to solve the orbitals of atoms, similarly, the same Schrodinger approach or Schrodinger wave equation can be used to calculate the energies and shapes of molecular orbital. So let's discuss what are the rules which are applied when we solve the Schrodinger wave equation during the formation of covalent bonds. Let's check the rules of molecular orbital theory. So first rule is combination of n atomic orbitals form a set of n molecular orbital, which means that the number of molecular orbitals formed is equals to the number of atomic orbitals combined. Second, just like atomic orbitals, molecular orbitals are arranged in the order of increasing energy. And finally, the third rule is that filling of molecular orbitals with electrons is governed by the same principles as the filling of atomic orbitals. For example, we will use the Aufbau principle, Pauli exclusion principle, and Hund's rule to fill molecular orbitals with electrons. The formation of a molecular orbital by the combination of atomic orbital is shown in this figure. As you can see, two 1s orbitals are combining to form a molecular orbital. So these two are also 1s orbitals, and these two are also 1s orbital. These are the same spherical s orbitals we learned about in a couple of slides earlier. Now, what's the meaning of positive and positive sign? And in this case, and if you see there's a negative sign on the blue and positive sign on the red, what does that mean? Now, the meaning is it's not charges. The signs are, remember, Schrodinger wave equation treats all particles as waves, and the positive means that the wave function is positive. Okay, so remember there's a positive wave function, negative wave function. So positive means that both of these orbitals are combining constructively. Do you remember that constructive combination and destructive combination? So similar to that. So constructively, they are combining with each other, and then destructively. So when they combine constructively, we call them adding with each other or addition. The resulting molecular orbital, this is the resulting molecular orbital. So the resulting molecular orbital is this one. So this is molecular orbital. These two are atomic orbitals. Now same two orbitals, if they combine destructively, these are the not two new orbitals, the same one. There are chances that the orbital waves can combine constructively and destructively, the same two orbitals. When they combine destructively, this will be the resulting molecular orbital. The molecular orbital which is formed by constructive addition or addition of atomic orbital, that molecular orbital is lower in, or it has less energy, so it's more stable. Stable means its energy is low. See, this way is the energy. And if the molecular orbital is formed by subtraction, so then this one is high in energy, so unstable. The molecular orbital formed by the addition of atomic orbital is known as bonding molecular orbital. So this one is bonding molecular orbital, and the molecular orbital which is formed by subtraction, such as this one, is known as anti-bonding molecular orbital. So in simple terms, you can remember that when two atomic orbitals combine with each other, they can either combine additively, or they can add to each other, or they can combine subtractively, or they subtract from each other. When they add to each other, they form a stable bonding molecular orbital such as this one, and when they subtract, they will form the unstable anti-bonding molecular orbital. So two atomic orbital will give rise to two molecular orbital. One of those molecular orbital will be bonding, the other one will be anti-bonding. Also, you can see here, let me clean this up. So the energy level of atomic orbital is here. So this is the energy level of atomic orbitals. And you can clearly see that the molecular or the bonding molecular orbitals are lower in energy. So they are more stable than the parent atomic orbital. And the anti-bonding are more unstable than the parent. So in a molecule, if electrons are present in a bonding molecular orbital, they will have lower energy than when they were present in the atomic orbitals. A sigma bonding molecular orbital is a molecular orbital in which electron density is concentrated between the two nuclei along the axis joining them, and is cylindrical in shape. You can also consider sigma bonding molecular orbital as a molecular orbital which is formed by the head-head overlap. Let me explain this in simple terms. Let's imagine we have hydrogen atom. So this is hydrogen atom, not a molecule, just atom. And we know that hydrogen atoms are highly unstable and they don't exist as individual atoms. Hydrogen always exists as H2 molecule, because H2 molecule is stable. Now, why do they form? Let me explain. So if this is my hydrogen atom, and ignore the nucleus because nucleus doesn't participate, and we know, and in each hydrogen atom we have one electron, and that electron is present in, if you write the electronic configuration, it's present in 1s atomic orbital, right? So this is the atomic orbital. And if nearby we have another hydrogen atom, so that's another hydrogen atom, and this hydrogen atom also has its electron present in its own 1s orbital, and this is the energy. So atomic orbital have energy something somewhere here, so that's the energy level of atomic orbitals. Now when these two atomic orbitals combine with each other, they will form molecular orbital. So this will be the, again, two atomic orbitals are combining, this one and this one, so two of them, so therefore we will form two molecular orbital. So one molecular orbital will be bonding molecular orbital, and it will be lower in energy. The other one will be anti-bonding molecular orbital. So this will be, there is a nodal plane. I'm not gonna draw it to the correct shape, I'm just gonna draw a box. So this is the anti-bonding molecular orbital. Molecular orbitals are represented by sigma, and it's formed from the combination of 1s, so the name of this is sigma 1s. And the antibonding are represented by sigma star because it's formed from 1s atomic orbital, so therefore its name is sigma star 1s. To begin with, we had two electrons, one from this hydrogen, the other one from this hydrogen. Now after the bonding molecular orbitals are formed, both of these electrons will have an opportunity to stay in this molecular orbital, so they will jump into this one, stay together, and you can see that after the combination, now they are together, so that's a covalent bond. This covalent bond is when there's a sharing of electron, so that's a covalent bond, and resulting covalent bond makes these electrons to go in the molecular orbital, and molecular orbital is lower in energy, therefore this bond formation will make the entire molecule to be more stable. Hence H2 is more stable than individual H atoms, and that's why individual H atoms do not exist, they form molecules, and molecular orbital approach clearly explains it. This figure explains the same principle which I explained in previous slide. Uh, the atomic orbital, so these are atomic orbitals, this one as well as this one, they combine to form molecular orbitals. So these are the molecular orbitals, so that's the upper one is anti-bonding and the lower one is bonding. In ground state, both the electrons will be in the bonding molecular orbital, but they can absorb energy such as from radiation to go to the excited to the upper level, so this is known as excited state. So in excited state, one of the electron from the bonding molecular orbital, such as from here, will go up to the anti-bonding, such as here. Let's talk about valence bond theory. The basic principle of valence bond theory is that the bonds are created by the overlap of atomic orbitals on adjacent atoms. Therefore, with valence bond theory, the bonds are localized between adjacent atoms rather than delocalized over several atoms, as we saw in case of molecular orbital theory. The valence Bond theory correlates with Lewis' picture where two electrons are visualized between atoms as a bond. To represent the bonds, lines are drawn between the atoms. However, localization of bonds between atoms present a problem for second period elements such as carbon, nitrogen, and oxygen. In forming covalent bonds, the atoms of carbon, nitrogen, and oxygen uses 2s and 2p atomic orbital. Let me show you with the help of an example. Let's imagine that we would like to see what kind of bonding exists in the molecule of methane. So in methane, we know that carbon gonna form a covalent bond with hydrogen. And it's a covalent bond, so therefore electrons must be shared. If we write the electronic configuration of carbon, it is 1s2, 2s2, and 2p2. So the overlap of orbitals gonna come from the 2s orbital and 2p orbital because these are the valence orbitals, right? So if this is the 2s orbital, we have 2 electrons here and 2 electrons here. So the first problem is carbon has only 2 unpaired electrons. How can it form 4 bonds? Well, the solution was proposed that one of the 2s electron jumps into the p orbital, 2p orbital, and now we have 4 unpaired electrons. Okay, uh, so sound of it kind of sounds okay. So let's see if that works. Now, because let's imagine the case of 3p orbital, and we learned previously that the p orbitals are perpendicular to each other. So if this is px, this is py, and then this is pz, right? So now we have 3 unpaired electrons. So one is sitting here and one is sitting here, the other one is sitting here. Now if the hydrogen is going to make a sigma bond, so that's the s orbital of hydrogen. So if these two gonna overlap, so the overlap will take place here with p orbital. So another one here, another one here, and the fourth one will be with s orbital. So let's ignore that. Now the problem here is that the p orbitals are at 90-degree angle. So the bond angles should be 90 if that's the case. If orbitals combine as such, if atomic orbitals combine as such. But we know that methane does not have 90-degree angles, right? Methane, we know that methane is tetrahedral. So therefore this picture is incorrect. So that's the problem with simple valence bond theory. So if these atoms use atomic orbitals to form bond, we would expect bond angles of 90 degrees, but these are not 90 degrees. So the theory did not end here. So it was proposed that in valence bond theory, atomic orbitals don't really combine as such. They undergo a process called hybridization. So in valence bond theory, atomic orbital combine with each other to form hybrid orbitals. Now, what are hybrid orbitals? Let's talk about that. Now, we have found experimentally that bond angles in organic molecules with single bonds are 109.5 degrees, which is tetrahedral, which is found in tetrahedral geometry. And the molecules who have double bond, they have bond angle of 120 degrees, and the molecules with triple bond have bond angle of 180 degrees. To account for these observed bond angles, Linus Pauling proposed that atomic orbitals uh, combine with each other to form new atomic orbitals. Those new atomic orbitals are called hybrid orbitals. Now, hybrid orbitals are formed by combination of atomic orbitals. And in order to combine atomic orbitals, mathematical energy calculations put some constraints. And according to those mathematical limits, atomic orbitals within the same shell can overlap with each other. For example, 2s can overlap with 2p because their energies are not that different. 2s cannot overlap with 3p, or 2s cannot overlap with 1s, or so on. So only those atomic orbitals can combine with each other to form hybrid orbitals who are kind of similar in energy. The number of hybrid orbitals formed is equal to the number of atomic orbitals combined. For example, if 1s and 3p orbitals combine with each other, so total 4 are combining, so we will get 4 hybrid orbitals. Okay, so although various kind of hybrid orbitals are possible, but we only gonna focus on these 3 kind of hybrid orbitals because these are the ones which we're gonna see in this course. So I'm gonna only focus on these 3. Now, what do we mean when we say that 1s and 3p orbitals will give us 4 hybrid orbitals? So let me explain. So this is s orbital, and if it combines with 3p orbitals, for example, so that's px, py, sorry, I'm kind of lost in space, so pz, right? So we have 3 different p orbitals, and they will result in formation of 4 hybrid orbitals. Now the shape of hybrid orbitals will be in between the parent molecule. For example, if s orbital is combining with p orbital, now s is spherical in shape and p is kind of like a dumbbell, so the resulting shape will be somewhere in the middle of 2. So it's kind of like a spherical ish dumbbell. So now in this case there are 3 p orbitals and 1 s, so the resulting orbitals will look more like p because there are more of p, and then less like s, so it would be something like that. So now we said that 4 orbitals will give us 4 hybrid orbitals, so these are the 4 hybrid orbitals. Okay, each of these orbital is known as sp3 orbital, each of this. So we have 4 sp3 hybrid orbitals which are formed because we combined 1s and 3p orbitals. Now we know that energy of s orbital is lower than the energy of p orbital. When these two combine, the resulting hybrid orbital will have energy somewhere in the middle, and all of these 4 hybrid orbitals will be at same energy level, and each hybrid orbital can hold maximum of 2 electrons, but they also follow the rules of Aufbau principle and Hund's rule. Uh, so that's why we see that before pairing up with 2 electrons, there are 4 orbitals available. So first each orbital is occupied by single electron. Now this is the hybrid sp3 orbital of a carbon atom, which is formed from 2 s orbital and 2 p orbital. 1 2s orbital and 3 2p orbitals. So like previously I explained that the p orbitals stay together even though we show them separately like that, right? So px, py and pz, but they are together. Similarly, when sp3 orbitals are formed, we have 4 of these ones. So 4 of these, they are not present separately, they are all entangled with each other, so they form a 4 of these will form a tetrahedral geometry. So these are 4 sp3 orbitals in tetrahedral arrangement. These are around nucleus, so nucleus is somewhere in the center, and each one in case of carbon holds 1 unpaired electron. So when each of this combines with hydrogen, so one hydrogen here, it brings its own electron, one hydrogen, so that's the 1s of hydrogen, it overlaps, that's the 1s of hydrogen, and that's the 1s of hydrogen. Now you can see that the bond angle between C, H, 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 and H is 109 degrees. So this hybrid orbitals clearly explains why the bond angle is 109.5 and not 90 degrees. Orbital overlap pictures of methane, ammonia, and water molecules are shown. If you see, there's a hydrogen 1s overlapping with the sp3 hybrid orbitals of carbon. The color choice is not that great in this picture, but I think you can still see. One thing to remember here is that in case of nitrogen, one of the hybrid orbitals contains the lone pair, and in case of water, two hybrid orbitals contain the lone pair of electron, and other two orbitals are used for bond formation with hydrogen. Let's look at the hybridization of 1s and 2p orbital, resulting in formation of sp2 hybrid orbitals. So as we saw previously, in this case also 2s orbital and two of the 2p orbitals. The third one does not participate, and these two results in formation of hybrid orbital, and these hybrid orbitals are called sp2 hybrid orbital because they are formed by combination of 1s and 2p. Now in this case, again, we are combining 1s orbital and 2p orbitals. So we are combining three total orbitals, so hence resulting orbitals will be 3 sp hybrid orbitals. They will be similar looking to the hybrid orbitals of sp3, but roughly the shape will look somewhere in between the spherical S and dumbbell shape P, and these three are shown here. Each of these hybrid orbitals will contain one of the electron. Remember, we are starting with four electrons. Now three of them will be in the hybrid orbital. The fourth one will stay in the unhybridized 2p orbital. So this is unhybridized. Just like in sp3, we saw that the four hybrid orbitals entangle with each other to form tetrahedral, but when we have three of sp2 orbitals, they will form a trigonal planar structure, and each of these will hold one unpaired electron. The unhybridized p orbital stays perpendicular to the hybrid orbital is shown here. In case of carbon, if it undergoes sp2 hybridization, each hybrid orbital will contain one electron, and the fourth one will be in the unhybrid p orbital. The covalent bond formation of BH3 or borane is shown here, and in case of borane, we have only three bonding orbitals. The unhybrid 2p orbital stays empty. The bond angle in BH3 is 120 degree because trigonal planar structure has 120 degree angle. In case of sp hybridization, 1s and 1p, so 1s and 1p will form the hybrid orbital, and the remaining two p orbitals remain unhybridized. So in this case, one s orbital and one of the p orbitals will combine, resulting in two hybrid orbitals, only two. The remaining two p orbitals remain unhybridized. And we know that when we have two orbitals together, they will entangle and form a linear shape. So this will be the shape of two sp hybrid orbitals. They are entangled with each other. So this figure explains what happens when you have two sp hybrid orbitals together. So they form this kind of shape. So one is here, the other one is here. The unhybrid p orbitals remain perpendicular to each other. So one of the p orbital is here, the other one is here. The hybrid sp orbitals are here. The hybrid sp orbitals kind of look like a p orbital, but remember, this is not p orbital, this is hybrid sp orbital. It's a little bit larger, and there's a part here, so that this is hybrid sp orbital. Valence bond theory views bonding as resulting from electron pair localized between adjacent atoms. These pairs create bonds. Further, we commonly use atomic orbitals involved in three hybridization states to create orbitals in order to match the experimentally observed geometry. In other words, the hybrid orbitals will explain the bond angles. But now the question is, how do we make orbitals that contain electrons? So what do I mean by that? The meaning is that, okay, so imagine we have the tetrahedral orbitals. Okay, so that's the tetrahedral orbital of carbon. And when it have to form a bond between hydrogen, so hydrogen is 1s here, and it's gonna overlap here. So when it overlaps, it's gonna make a new orbital, right? How do we make it? What does it look like? Why would it overlap? And if it does overlap, what would it look like? To answer all these questions, we again turn back to molecular orbital theory. Because valence bond theory cannot explain why would now 1s overlap with the hybrid orbital of carbon. So now we have to go back to molecular orbital theory. So that's why the bonding in organic chemistry can only be explained by using combination of valence bond and molecular orbital theory. To create new orbitals that are localized between adjacent atoms, we add or subtract the atomic orbitals like we did in case of molecular orbital theory. Now only those atoms are added or subtracted which are aligned to overlap with each other. For example, in case of methane, the sp3 hybrid orbitals of carbon and 1s orbital of hydrogen are aligned, so therefore we add or subtract these orbitals. So what I'm trying to say here is that if this is the sp3 hybrid orbital of carbon, each one contain one unpaired electron, and only aligned atomic orbital, this is aligned with one s orbital of hydrogen, so these two orbital will uh, add or subtract. So now again we are going back to the Schrodinger wave equation and the molecular orbital theory concept, that these wave functions of this hybrid orbital and 1s orbital will either add or subtract to give us the bonding molecular orbital and anti-bonding. Like we saw in previous example when we were discussing molecular orbital theory, when two atomic orbitals overlap to give a molecular orbital, we get a bonding molecular orbital which is lower in energy. and anti-bonding molecular orbital, which is higher in energy as compared to the parent atomic orbital. So similarly, when these two will combine, the bonding part of these two orbital will be more stable than either of these two parents. This figure shows the molecular orbital mixing diagram of a carbon p orbital, or the electrons which are in p orbital. So these are atomic orbitals, these two, this one and this one. When these two atomic orbitals combine, they will result in two molecular orbitals. The bonding molecular orbital, which is sigma, will be lower in energy or more stable, and the representation of the molecular orbital is shown here. So the electron density is concentrated in the middle of two nuclei. So that's the bonding molecular orbital. On the other hand, the anti-bonding molecular orbital, you'll see that there is no uh, electron density is not concentrated in the middle of nuclei. So that's why it's anti-bonding, because it's away from the two nuclei. There's no bond here. So that's the anti-bonding. That's why it's higher in energy. So the valence bond theory explains the angles, and the molecular orbital theory explains the bonding between two adjacent neighbors. For example, this bonding, you can see this is the bonding molecular orbital in case of ethane, right? So that's more stable. So this overlap of these orbital cannot be explained with valence bond theory. So because it's a had overlap, so that's the sigma bonding molecular orbital, and this came from the molecular orbital theory. But the shape of this molecule, which we know that this is a tetrahedral shape, so angle is 109.5 degree, and the skeleton structure is shown here. So that concept came from the valence bond theory. So now you can see that the combination of both valence bond and molecular orbital theory explains the bonding as well as shape and bond angles of organic molecules. Organic molecules with a double bond use sp2 hybridization. In sp2 hybridization, we know that 1s and 2 p orbitals combine to form 3 sp2 hybrid orbitals, and they are arranged in such a way that the shape is trigonal planar. So these show the 3 trigonal planar sp2 hybrid orbitals. And each one contain one electron, and that's the second carbon. So same way, second carbon also has the sp2. Now sp2 hybrid orbitals overlap with hydrogens to form sigma bond. So that concept, as we explained, came from the molecular orbital concept. Now we also know that one of the p orbital remain free or unhybridized. So that's the unhybridized p orbital. So let me clean up a bit. So remember the this grayish section are the hybrid orbitals. The red and blue one, these are the unhybrid orbital. Now unhybrid orbitals also contain one unpaired electron, and this one also contain one unpaired electron. Now in this diagram, it's not possible to show them together, but in actual practice, they are much closer to each other. So when they are closer to each other, they overlap sideways to each other. So this sideways overlap creates a pi bond. And this I'm showing, it's not a triple bond, by the way. I'm just showing that this whole entire thing overlaps sideways. So that creates just one pi bond. So in a double bond, one of the bond will be a sigma bond, which is created by the head-head overlap of sp2 hybrid orbital, and one pi bond, which is created by the side overlap of unhybridized p orbital. And the bond angles between carbon and hydrogen bonds is 120 degree, which is usual for molecules with trigonal planar shape. This figure shows the molecular orbital approach to show how the sideways mixing or overlap of atomic p orbitals creates a pi molecular orbital. That's a bonding pi molecular orbital. The electron density is dispersed or localized throughout the molecule or overall. And in case of antibonding, the electron density is away from the bonding part, so that's why it's in the it's antibonding molecular orbital.